Hello and welcome to this lecture on introduction to copulas. We started this section, this copula in the last class, and we covered up to the dependence, and today's class also we will cover and we will continue the same topic. In this lecture we will start with their dependence properties, and after that we will discuss specifically about one specific group of copulas which is so far used and has seen applications in civil engineering, particularly in the hydrology and water resource engineering. So, we will discuss that class of copulas and we will see some problems after that. So, our outline, if you see that outline of this lecture today, that we have already you know that in the last class we have covered this definition and explanation of what is this theory of copula, and after that we have discussed some of the properties of the copula function that it should satisfy to be a copula function. And as you know that when we are transforming from the one dimensional to the multidimensional cases, so there are some of these basic terminologies, the meaning of the basic terminologies also should be extended to the higher dimension. So, regarding that we have discussed some more terminologies. For example, the grounded we have discussed what is the H volume and what is the two increasing function. So, those are the properties that should be satisfied by a function to before we can declare that function to be a copula. And after that we also discuss about the Sklar theorem, and while discussing this one we have we told that this is basically the most important theorem in this one, where we can use the function copula to develop the joint distribution from their marginal distribution. And we also started the discussion on this measure of dependence, and today basically we will start from this measure of dependence from the copula function, and also we will see that how to get those dependence parameter from the samples. And after getting that sample dependence, then we will go and we will see that how those parameters can be used, means from those parameters how we can obtain the parameter for the copula function. So, that we will see, and after that we will see example on these copulas. So, as was discussed in the last class, that there are two main measure of dependence, and those are we will be using in this, and these are the expression for those. First one is the Spearman's correlation coefficient or the Spearman's rho, and this rho s is equals to the 12 times of this double integration with respect to the copula function minus 3. So, this expression gives you the Spearman's rho, and similarly the Kendall's correlation coefficient or the Kendall's tau, which is the 4 times the integration of this copula function with respect to that function c minus 1 gives you the Kendall's tau. And we have also stated that this tau and this rho s follow this relationship, means through this inequality this is. So, minus 1 less than equals to 3 times tau minus 2 times rho s, which is less than plus 1. So, this 3 times tau minus 2 times rho s is bounded by minus 1 to plus 1. But what is more important here is that the expression that we have explained here, this is in general for all the copulas, whatever may be the class. Now, you know that even though this we can explain it very mathematically, we can explain it rather easily, but for some of the cases it will be better if we get some more what to say, that easier form of this function. So, that means those are basically the in the mathematical point of view, those are more easily can be applied, and one such case is the Archimedean copula that we will be discussing after this, how these expressions, means this expression will be changing depending on what the copula in hand. So, this Archimedean copula, so one special class of this copula, the definition of this Archimedean copula is stated through this, that a copula that can be expressed in terms of this CUV, this is the copula function, is equals to that phi inverse of phi u plus phi v. Now, you know that for the bivariate case there are two variables, one is the u and v, and now there is a function which is that phi. So, it can be it is the first one is that phi u and second one is the phi v. So, the functional form of this phi is same. So, if we add them and then we take one inverse, this inverse is known as the pseudo inverse, we will explain in a minute. So, if we can explain that full function in this form, then that class of copula is known as Archimedean copula. Now, this phi, this function phi, this is a strictly increasing continuous function. So, you know that this strictly increasing means it is if we take two values, one is that u1 and u2, and if the u2 is greater than u1, then phi u2 should be greater than phi u1. So, that is the strictly increasing, and means strictly increasing when we are saying that time that equality sign also is not there. So, earlier in when we are discussing the two increasing, you know that we are discussing, or in case of the one dimension that single random variable while describing the CDF, we are explaining that it is non decreasing. So, the difference between the non decreasing and strictly increasing is that non decreasing means there my equality sign is included. So, that if that the second value is greater, that is u2 is greater than the u1, then if the functional value at u2 is greater than equal to that the functional value at u1, then we say it is non decreasing. So, that equality sign is also included. Now, the strictly increasing means that equality is also not there, it has to increase if the attribute increases. So, that is, so this is the functional property of this phi, this is that strictly increasing and this is a continuous function, and that phi in straight bracket written -1, that is a phi inverse, which is known as the pseudo inverse of that same function phi. And this function actually, you know that now once we can express that full copula function in this form, that means here one function that is most important is this phi function, and if we know that what is this phi function, then we know what is the copula function also. So, that is why this phi function is known as the generator of this copula. So, phi is known as generator of the copula, and this pseudo inverse, as we are as we are just expressed that the pseudo inverse of this phi of this inside whatever we have written, that phi u plus phi v. So, this pseudo inverse is explained in this form. So, this pseudo inverse is equals to its inverse, this -1 when you write without this straight bracket, it is the inverse function only. So, it is the inverse of that function as long as this t is in between 0 and phi 0. So, whatever the function we get, if what is the value at 0 of that function, from 0 to that value, as long as this t lies, then we take simple inverse of that function, and beyond that range, that is from phi 0 to the infinity, it should be 0. So, this is actually what is the pseudo inverse means. Now, we will see some of this example of this Archimedean copula along with their generator phi, then it will be more clear. So, so if we just take one example of that generator, suppose that what that phi function that we are taking, that we are just now we have stated, is this 1 minus theta 1 minus t power theta. Now, theta is one parameter, we will come to this parameter a few minutes later. So, suppose that this function with one parameter theta is explained through this 1 minus t power theta, where this theta can vary from -1 to infinity. Now, if we take that phi 0, means phi at t equals to 0, then we can see that this the value of this function should be equals to 1. Now, if we follow that this pseudo inverse of this function, that is it is 0 to that phi 0, that is phi value at 0, then this is becoming 1. So, we have to take the inverse of that function at 0 to 1, and from 1 to infinity it should be 0. Now, if we take the simple inverse of this phi t, then it is 1 by, you know, that it is 1 by this phi function. So, this will be 1 minus t power minus theta, and for the rest area, that is from 1 to infinity, it should be 0. So, this is the complete definition of the pseudo inverse of the function phi t as explained this functional form. Now, this function, if this function changes, obviously our pseudo inverse also will change. Now, if I want to know what is the copula through this generator, now this C u v, what we have to write is that C u v is equals to that pseudo inverse of that function into that phi u plus phi v. Now, this is just we are changing that that attribute, that is it is phi u. So, it is 1 minus u power theta and 1 minus v power theta, and for this form we have to take its pseudo inverse. Now, if we want to take its pseudo inverse, then we have to take that one 1 minus t power minus theta. So, this is 1 minus whatever there in this full expression, this expression, then full that power minus theta. So, this is explained, and for the rest of the places it is 0, and this one you know that is from this 0 to 1. So, this functional form what we got is one copula, and this is definitely one Archimedean copula. Why it is Archimedean copula? Because we can explain it through this one, and for this Archimedean copula the generator is 1 minus t power theta. Now we will see this these functions are having some names depending on who has first invented this these functions, proposed this function. Depending on that, there are many such Archimedean copulas, and you know that for each function, what is the one function that is controlling everything is this one, this phi t, which is the generator of this function. So, depending on that, if the phi t changes, we will get a new Archimedean copula. Now, this Archimedean copula has found its popularity in different field of research, including the different areas of civil engineering. Particularly, if you see so far we have seen many applications in this hydrology and water resource engineering. And why this Archimedean copula has become the reasons why these are become popular is that it can be easily constructed, as you have seen that one example that just now we have discussed. So, these things can be easily constructed, and for this one the many varieties are available depending on its dependence. So, what is the nature of dependence that it can, or the range of dependence that it can capture. For the time being, I can mention that the theta function that I was mentioning, this is actually the measure of the dependence between the two random variable that we are considering here, and the reduced variables u and v. So, their dependence, so this is the range of their dependence. Now, so as we can have many varieties. So, depending on our requirement, whether there is a positive dependence, negative dependence, very narrow range of dependence. So, we can pick up whatever which Archimedean copula we wish to take. So, there are a lot of varieties are available in this class. This Archimedean copula is one class among which different copulas are available. So, we can pick up depending on our requirement of the problem. And they possess some nice properties. So, we will just explain how, because as I told that this theta is here is the parameter which is controlling the dependence between u and v, and just few slides before we have also discussed that Kendall's tau, and which is a measure of dependence. Now, through this Archimedean copula, we can show, we will just show in a minute, that this can be related to each other through a nice expression, and that actually is giving that form, that how to obtain that theta from that tau. So, our steps will be now, if we have the data, first of all we have to see the data follows which distribution, and from the sample data we can also calculate that what is their Kendall's tau, or those measure of dependence, and from the tau we have to determine that what is the parameter for the copula that we have taken, and if we know that copula, then the full form of this joint distribution is known to us. So, this is one, this could be the complete step, and depending on this theta, as I was telling, that theta, it actually depends on what value of this theta, that is the dependence measure, what value of the theta you wish to take, and depending on that it can change a lot. Say for example, here another example of this copula function is shown here, which is the maximum of u power minus theta plus v power minus theta minus 1 comma 0. So, maximum of these two power minus 1 by theta, and here this theta, that is the dependence parameter, which belongs to this minus 1 to plus infinity excluding 0. This is the meaning of this full form. This is the dependence can range from minus 1 to plus infinity, that 0 value is excluded in this range. And if, as it is an Archimedean copula, you know that there should be one generator. So, this phi function, obviously the t is the attribute which is not shown here, just for this simplicity, that is phi theta, theta is the parameter of this dependence. So, this generator of this copula is that 1 by theta into t power minus theta minus 1. Now, here the two figure that you can see, so this we can generate. I will just explain how we can generate these values. This is the combination of this u and v. So, scatter plot between u and v, say that this x axis is your u and y axis is your v. Now, we can assume some theta just to see that how their scatter plot look like, so that we can assess some kind of dependence. So, this is for this 0.8 or so, this theta value, whereas this one is for, if we change the theta to say 0.5, if we change the theta to 5, so which is a high dependence, dependence parameter is higher. So, this is for the theta equals to 5 and this is for theta equals to 0.5. So, you can see that when the theta is less, then we can get the dependence pattern can change significantly depending on what the theta parameter, the dependence parameter is opted for. And this is one of the positive thing of having a wide range of dependence. You can see here it is from the minus infinity to the plus, it is from the minus 1 to plus infinity. So, the wide range. So, we can model depending on whatever the data is available to us, we can model a wide range of dependence between the two random variables. So, now we will see that how this Kendall's tau that I was talking, that this Kendall's tau is related to their parameter, that theta parameter, if it is an Archimedean copula. Now, remember that whatever the expression that we are going to express is that this is for in case the copula is the Archimedean copula. So, earlier the expression that we have seen, that is for the general, as I mentioned, that is for the general expression for any copula, and from there depending on the whatever the special properties that class is having, we can reduce that relationship to some other form, some other easier mathematical form. So, here the example for that Archimedean copula. So, the first line very straightforward is that in case of Archimedean copula. So, in case of Archimedean copula, this Kendall's tau is reduced to this form, that is 1 plus 4 times integration from 0 to 1, that phi u by phi prime u. This phi prime u is the first order derivative of that function with respect to u, and this phi u, you know that this is the generator of this function, and that we will integrate definite integration from 0 to 1, and that 4 times plus 1 gives you the form of this tau. Now, you know that this in this form there is the parameter theta is there. So, that theta will be there in this expression, and left side that is tau. So, here what we can see is that there will be a relationship between this tau and the theta, where the theta is your measure of the parameter that is capturing the dependence between two random variables. Now, so what we have to do first from the sample is that we have to estimate what is the value of tau, and that is the Kendall's tau, and this Kendall's tau, if we know from this data, then we can estimate that sample estimate, we can get the sample estimate of the theta, and that theta we can use for the complete development of the joint distribution. Now, we will take some time to explain what is how we can get that sample estimate of Kendall's tau. This sample estimate of Kendall's tau, this is tau cap, is equals to that xi minus xj multiplied by yi minus yj greater than 0 minus xi minus xj into yi minus yj less than 0 for all I j where I and j are not equal. So, this may be the mathematical expression. Let me explain that what it means through two basically the first probability that we are talking about, this is the concordant pair. So, xi yi comma xj yj, these are the two pairs of this of the sample, and if this relationship holds good, that it is greater than 0, then we say that it is a concordant pair, or if this relationship holds good, then we say this is a discordant pair. So, I will just explain here how this thing from the data how it looks. So, suppose that there are two that random variable that we are talking about, and we are having some data available to us. So, this is the first entry, the first entry of this x and the first entry of y. So, this is paired. So, this is basically what we are talking about. This is say the x1 and this is y1. Similarly, this is x2 and this is y2. And like that we are having n data set xn, and this is say yn. Now, to know that what is the Kendall's tau between these two series is there. So, what we have to take, we have to just pick up two pairs out of these n pairs. Now, two pairs out of these n pairs means so you know that, so total pair that we will have is that NC2, that is n combination 2. Out of n pairs like this, how many ways you can pick up 2 pairs. So, this is the total possibility. Now, after you pick up, say for example, you are taking the first pair and the second pair. Now, you have to know whether these two pairs are concordant or discordant. Now, if this x2, suppose, so the if I just take this to 1. So, if say that x1 is greater than x2 and y1 is greater than y2, or x1 is less than x2 and y1 is less than y2. So, if this one increasing, this should also increase, or if this is decreasing, whether this is also decreasing or not. So, that the trend, that is the way it is changing, whether in both the cases it is changing in the same direction or not. If that is so, then that means this is what is explained through this mathematical form. Then these two pair x1, these two pair means the x1 comma y1 and that x2 comma y2. So, these two pair is supposed to be the concordant. These two pair is said to be the concordant. Now, if the opposite thing happens, say that if that x1 is greater than x2 and y1 is less than y2, or x1 is less than x2 and y1 is greater than y2. So, if this relationship holds good, then that pair x1 y1 and x2 y2 is known as discordant. So, now if this one, so now if you see that, now how to test it through that, suppose we can just see whether just by visual inspection also you can see, or what we can do is that we will, if we take that x1 minus x2, if we just want to combine both these conditions together, then we can say that if the x1 minus x2 multiplied by y1 minus y2 is greater than 0, you see, if it is greater than this and this is greater than this, then the multiplication also will be greater than this, or if this is less than this and this is less than this, then also x1 minus x2 multiplied by y1 minus y2 will be greater than 0. That is why it is written here that if that xi minus xj multiplied by yi minus yj is greater than 0, that means it is a concordant pair. And if the opposite thing happens, for example, here what we have shown that it is greater than and it is less than, it is less than and it is greater than, then what will happen? This is the discordant. So, their multiplication x1 minus x2 multiplied by y1 minus y2 will be less than 0. So, in this case this is discordant. Now, this Kendall's tau is the difference between the probability of concordant pair minus probability of discordant pair. Now, out of this n pair that is available to us, we know that there are total way that we can select two pairs is the NC2. Now, out of this NC2 choices, there could be few choices will be the concordant and few choices will be discordant. Suppose that total number of concordant pairs is C and total number of discordant pair is D. So, where the definition says there is a difference between the probability of the concordant pair minus the probability of the discordant pair, that means the probability of concordant pair from this sample, what is that? It is C by NC2 and probability of discordant pair is D by NC2. So, if we get this one, then this will give the estimate for the Kendall's tau from this sample. Now, there could be one thing can also happen, that is if that x1 is equals to x2 or that y1 is equals to y2. So, because this is a sample, this can happen. In those cases we generally exclude those pairs. So, that is why, so the C plus D is in the ideal cases, if both are the continuous random variable and the probability of being exactly equal to the other output is 0 from the theory point of view, but from the sample it can happen that x1 is equals to x2 or some pair is equals to x2. So, if they are not equal, there is no entries are equal for both the cases, then ideally C plus D is equals to your NC2. But as there could be some possibilities of the equality, then this is basically C plus D is less than equals to NC2, one or two combination that has to be ignored. So, after ignoring that one, you will get that C minus D divided by NC2, and that is giving you that what is the estimate of this Kendall's tau, and this is what is explained here. This C and this D are the number of concordant pair and this is the number of discordant pair. So, this is the C by NC2 is nothing but your the probability of concordant pair, and this is the probability of discordant pair. Their difference gives you the Kendall's tau. Now, we from the sample we got how to get their sample how to know their sample estimate of the Kendall's tau. Now, we will see that how this sample estimate can be linked to that theta, because we have already seen the expression that if that theta theta and tau are related to that one form in case of the Archimedean copula. And before that we will just discuss about a few Archimedean copulas. So, we are in the class of Archimedean copula. What we are showing you now the different possibilities. Few slides back I mentioned that there are many varieties are available, and their range of their dependence also varies widely. So, here some 4 examples, 4 different types of Archimedean copula are picked up for the discussion. The first one is the Clayton copula, for which the form of this copula is the maximum of u power minus theta plus v power minus theta minus 1 comma 0. So, out of these two, which one is maximum? That power minus 1 by theta. So, this one just few minutes back also we discussed, and so this copula name is your Clayton copula. And this one as its is the form of its generator is your 1 by theta multiplied by t minus theta minus 1. So, this is the generator of this copula, and the last column is giving you the range of their dependence, as this is already stated that this range is from this minus 1 to plus infinity excluding 0. The second one is the Frank copula, for which the expression for the copula function is minus 1 by theta log natural of 1 plus e power minus theta u minus 1 e power minus theta v minus 1 divided by e power minus theta minus 1. And for this Frank copula, its generator is minus log natural of e power minus theta t minus 1 divided by e power minus theta minus 1, and its the range of this dependence is minus infinity to infinity excluding 0. Now, as you know that as these generators are given and generator function is given, and these are the Archimedean family. So, what you can do is that you can take this generator and fit into that form, this form, and we can see that whether you get that copula form or not. So, we have in the example we have discussed this copula, which you will see here now. This is the okay. So, that one is one copula which is not listed here, that is also one of this Archimedean copula. So, the next one, after this Clayton and Frank, it is the Ali Mikhail Hawk, and this copula form is u v divided by 1 minus theta into 1 minus u into 1 minus v, and its generator is log natural of 1 minus theta into 1 minus t divided by t. And if you see its range, it is from this minus 1 to plus 1, 0 is included, but this plus 1 is an open boundary, and minus 1 is a closed boundary. You know, this open boundary means it is not exactly equal to 1, but mathematically it is very close to 1. So, this is their dependence range. So, the difference between these first two, that is the Clayton and Frank, is that for these two that dependence range is very wide, but the 0 was excluded. For the Ali Mikhail Hawk, the dependence range is very narrow, but 0 is included here. And the last one, that is the Gumbel-Hogarth copula, for which that copula form is exponential of minus of that minus log natural u power theta plus minus log natural v power theta whole power 1 by theta, and its generator is minus ln t power theta, and its range of dependence is the 1 to infinity. So, you can see here, this is one example where only the positive dependence can be modeled. So, even the positive means it starts from 1 only, so not even from 0. So, only the positive dependence can be measured. For the Ali-Mikhail-Hawk, the dependence range is narrow, but it is close, but it is narrow at 0, but it includes 0. For the Frank, it is the most wide range from the minus infinity to plus infinity, but the 0 is excluded. For the Claton, it is minus 1 to plus infinity, again that 0 is excluded. Now we will see how this function, we have seen that this one divided by its first derivative and definite integral from 0 to 1 4 times, and it has been added with 1 to get that tau, to relationship with this tau. What I am telling is this one. So, this Kendall's tau equals to 1 plus 4 times 0 to 1 phi u by phi prime du. So, we will just see for this 4 Archimedean copula how that thing is related with the tau. Here is that thing, here is that example, that is for the Claton. We have seen just in the previous slide that its generator is 1 by theta t power minus theta minus 1, and if we fit in that equation, we will get that this tau is equals to theta by theta plus 2. Similarly, for the Frank, it is that minus log natural of this e power minus theta t minus 1 divided by e power minus theta minus 1. So, these are the generator which we have already discussed here. Now, here what we are showing that with this one, if we feed this generator in this equation, then how this relationship between tau and theta comes. And for the Frank, it comes that this is tau is equals to 1 minus 4 by theta d1, this is a function again, d1 of this minus theta minus 1. So, so you can see that this is the full expression with respect to theta, and which is equated to tau. Now, this d1, before I go to that one, this d1 is known as this first order, this 1 stands for the order, the first order Debye function. Now, what is this first order Debye function is explained here. This is 1 by x 0 to theta t by exponential t minus 1 dt in case the theta is greater than 0. Otherwise, if for the negative one, that theta minus d1 minus theta is equals to d1 theta plus theta by 2. So, if it is negative, if the theta is less than 0, then we have to convert it to this form, then this one will be expressed through this one. Basically, for the negative one, this one plus theta by 2 it will come. So, from this expression you can see that maybe this one will not be will not have any closed form solution, but numerically we can solve that one. But for the other one, the first one, the Claton, we can this tau, if we know, then it is very easy to solve what is the value for the theta. Similarly, for the Ali-Mikhail-Hawk, that the generator is log natural of 1 minus theta into 1 minus t divided by t, and for this one that tau is equals to 3 times theta minus 2 divided by theta minus 2 by 3 into 1 minus 1 by theta whole square, log natural of 1 minus theta. So, this is the full form of that tau is equals to this one. And last one is the Gammel-Hogard, for which the generator is minus ln t power theta, and following the same equation, this tau will be equal to theta minus 1 by theta. So, now it is known that from the sample estimate we can have the tau first, then we can have the estimate of this theta, and that theta we can feed into that whatever the copula function tentatively used, that we can feed, and then we can get the joint distribution. Now, after getting the joint distribution, sometimes it is essential that so if you use only one copula function, obviously you will get one, and now the depending on the choice of which copula function you are using, so that way that your joint distribution may change. So, this is one of the question mark, but there are some methodologies available for which how to test that fitness, which copula is the best fitting the data. For example, this is also not uncommon in the sense in the single random variable. if we have a data, we generally go for the test that how this data is going to fit in the for which distribution. Okay, so that time also we have to pick up some several distribution. We have to see that for which distribution the data is fitting properly. Similarly, here also if we just take more than one copula function, then we can test that which one is fitting the best. We will take one example of this of the hydrology, particularly the hydroclimatology problem, to discuss that whatever the theory that we have explained so far, and we will see that this theory is applicable in a stepwise fashion. We will explain, and finally it is going to some of this prediction problem. But so far as the scopula is concerned, this is we can as long as we can get that their joint distribution, up to that we will see, and after that one slide is there for that prediction one, but that is the further taking of that particular outcome. So, the example that we are going to discuss is on this copula based method to capture the scale free dependence pattern. So, this one, as we have discussed, that first one, the first step that we should do whenever we are having some data, we will estimate the what is the sample estimate of the Kendall-Stowe of this data. So, this is the form that we have discussed, and in the step 2, that sample estimate of the Kendall-Stowe and plugged in the following equation, because as we are using that Archimedean copula, so you know that this equation should be plugged in, that tau estimate. So, we will get the estimate of this theta for a particular copula. Now, what we have to do, we have to generate some of the simulation of the particular copula. So, one copula we have taken, we know what is its dependence parameter. Now, if we can simulate that so one joint distribution is there, we have to simulate that one, preserving their dependence pattern. So, this one is that are the steps. So, first of all, we know what is this generator what is the generator, that is the phi, and from that phi we have to obtain that this pseudo inverse, its first derivative and its inverse of the first derivative, and then we generate two series. One is u, which is one uniform distribution which between the 0 and 1, and another one is the t uniform distribution again from 0 to 1. So, this u and t will generate independently. So, thus u and t have totally independent from each other. Now, we will generate another another series out of this u and t, which is that s is equals to that first derivative of this generator of that u divided by that t. So, each point if I just divide, and then from that s, if we take that its inverse of the first derivative of that s, then we will get one series, that is w. Now, this v is equals to that pseudo inverse of that generator phi w minus phi u, and this will give you the another new series which is v. Now, the pair u and this newly generated pair v, these are the simulated pair preserving their dependent structure. Now, this dependent structure here means that through the parameter theta, which is there in this generator function, then u and v are transformed by the inverse cumulative distribution function to get there in the original scale. Now, this original scales means that first of all say that we are having the two data set which may follow some distribution, it may normal, log normal or gamma, whatever. So, from that distribution I can first get their reduced variate, which are u and v. Now, from that, now whatever we have generated here, that u and v, these are those reduced variate, but they preserve their dependent structure. Now, that u and v can be transformed back through that inverse cumulative distribution function to get that in that original scale of the random variable. Now, in the step 3, as I was discussing, that the selection of the most appropriate copula. So, that is, there are two estimates. One is that parametric, that is the kz is equals to z minus phi z divided by phi prime z. Now, phi prime is the first derivative of that generator, putting that z as the variable. So, this one is the parametric estimate of their cumulative distribution, and the non-parametric is also we have to use it from the data that is available to us, that is a fraction of zi which is less than z. You know that for this is basically the cumulative distribution how we get from this data. Now, this zi is equals to that number of xi ji such that xi is less than xj is less than xi and yj is less than yi divided by n minus 1, where this I varies from 1 to n, j varies from 1 to n, but I and j are not equal to each other. So, in this way we will get both the estimate, that kz and this knz, one is parametric, another one is non-parametric. Now, this this knz is scatter plot. If we just prepare, that is kz and knz, if we have selected that copula correctly, then these two should be in such a way that it should be a straight line through the origin, which makes 45° angle with the origin, if these two are ideally same. So, it says that the better the fit, closer the corresponding scatter to a 45° line through origin, lowest value of the sum of square error from the 45° line through the origin. So, that has to be picked up as the best one. Now, after selecting the best copula, is a large number of the jointly distributed values are numerically simulated. These values are back transformed by using the corresponding non-parametrically estimated cumulative probability density, keeping any observed value of the that here as I was telling, that is a hydroclimatic problem. The climate precursor at the center, a sufficiently small window around it is selected. Statistical properties of the simulated values of the response variable lying within this window are investigated through the box plot. The median of these values is used as a prediction corresponding to the observed values of the climate precursor. The interquartile range, the 75th percentile to the 25th percentile of these values are indicated as the associated uncertainty. So, this is the last step, as I was telling, that is the further taking through this one, but as long as you get their joint distribution and you are able to simulate the large number of that joint pair, preserving their dependent structure. So, this preserving the dependent structure is the most important thing here that we are telling. So, we will just go through quickly that problem that we are talking about. So, this you have to for the detailed discussion you have to refer to one journal paper that I will tell you later, but for this one is that there are two time series has been taken. So, the problem is basically the bivariate here. The monthly all India rainfall is the one time series, and other one is the combined index between this ENSO and Equino. This ENSO is the El Nino southern oscillation for the tropical Pacific Ocean, and this is the equatorial Indian Ocean oscillation, which is a atmospheric phenomenon over this tropical Indian Ocean. So, there are background how we get this combined index. This combined index for the ith month and jth year is your that kappa month lag of this ENSO index and this lambda month lag of this Equino index multiplied by C1 C2, and these values also obtained from other analysis C1 C2 and this kappa and lambda. So, finally, by using this parameter and using these indices, we get one another time series, which is Ci, which is known as the combined index. So, we have the all India monthly all India rainfall and we have the combined index. So, two time series is available to us. Now, we have followed those steps and we have used 4 different Archimedean copulas here, and these 4 panels that you can see are for the 4 different copulas. One is the Frank, Clayton, Ali Mikhail Hawk and Gumbel-Hoggard. Now, you can see that what you can see here are the 3 different colors. The first one is the blue circle. These blue circles are the data points that has been used for whatever the calculation we need for this Kendall's tau and its theta estimation, and from the respective copula how we get their joint distribution. and after that we have simulated through that joint distribution that we have developed, and that simulation is shown by this gray cloud, these dots, gray dots, and over that we have overlaid some unforeseen data by this green star. So this was basically used for the validation. So this is covered by this cloud. So similarly, for all these three copulas, we have used the same procedure, and you can get this one. Now the second is the which one we should pick up from this one. So for that one, we have just a non-parametric estimate and the parametric estimate, and we plotted through this scatter plot, and their SSE, the sum of square error from this 45-degree line, is obtained, and these are the values is shown here. So this one you can see that the Frank one is the best because this is the closest to the 45-degree line, and using this Frank, this is how the joint distribution between the rainfall anomaly and the combined index looks like. And after this one, the finally what we have seen is that this is that prediction one, the last step that we are talking about, which is may not be the in the main focus of this theory of copula that we are discussing in this class, but for this further of this whatever the problem we have discussed, for the further references you can refer to this publication, the probabilistic prediction of hydroclimatic variable with non-parametric quantification of uncertainty. It is in Journal of Geophysical Research Atmosphere by American Geophysical Union. This reference you can refer to. So what I want to mention here at the end of this the brief introduction of this copula is that this copula itself is a wide area, and it is not possible to capture the everything in these two lectures that we have covered here. So further studies you can have in the different textbook that is available for this on this copula. And so far as the application is concerned on this copula is that these are very recent and mostly in the research area. So one of the example is shown here, and you can refer to some of this recent publication for its various application of this copula in the different field of research, including the different field of civil engineering. Thank you very much.